Okay, here we go. Question number 10. So, to the nearest whole number, what is the approximate square root of 200? So, remember when we were approximating square roots, we can kind of think of it helps to sort of think of these two different sort of number lines, right? We can line these up. And this is going to be here, for example, on the ball, let's say on the top, a perfect square, like 81. Okay, we know that comes from squaring the number 9. So if I square that, okay, if I go here, if I square that, 9 squared gives me 81. Or if I go in reverse, if I take the square root of this number here, I come down to this number line, square root of 81 is 9. So it's asking for we're looking for the square root. Okay, so that means we're looking for this number. Between 81 and 9, if we were asked the square root of 81, we're looking for this number here, 9, right? Okay, let's look at another easy one. We know that 10 squared, 10 times 10 would give us 100. All right, so now if I asked you to get the square root of something like, let's say 92, okay, and I want the square root to the nearest whole number. Well, 92 would sit somewhere between 81 and 100, but much closer to 100, right? So if we look down to where that would be on when we take the square root of it, it'd be somewhere here, maybe 9.6, maybe 9.7, oh, 67. Doesn't matter what it is. Let's just say it's 9.7. We don't need to know to estimate the exact number. We just want to know to the nearest whole number. Well, what's closer to 9.7, 9 or 10? It's going to be 10. So our square root to the nearest whole number would be 10. So it's just like saying, what is my closest perfect square to that number? If I know my closest perfect square, I'm just going to use the square root of my closest perfect square. Okay, my closest perfect square to 92 is 100. So then I can easily get a whole number like 10. Okay, so we're just working with a kind of bigger number. I started with this example because we can easily, we know these numbers, these perfect squares, right? But going beyond 10, maybe we don't quite know those. So we're at 100. We're going to have to try something. We get 81 by saying 9 times 9 and 10 times 10, right? So I could maybe try multiplying 11 or maybe 12. I'm just going to guess it's somewhere a little bit bigger. I'm going to try maybe 13, okay? Because I don't want to be doing math forever. So I don't have these memorized. So I'm going to try 13 squared, which is the same as saying 13 times 13. Okay, so maybe we're going to do a little bit of multiplication as we're used to seeing it. I might need more room. Okay, let's do that. Let's do that here. Okay, so we could write that as 13 times 13. And we've got 3 times 3 is 9. 3 times 1 is 3. 1 times 3 is 3. 1 times 1 is 1. We add that all up. We get 9, 6, 169. Okay, we're getting closer to 200. I don't know if this is the closest perfect square. I'm going to try another number. Okay, so let's go with 14 squared. Okay, so 14 squared is going to give us 14 times 14. 4 times 4 is 6. 4 times 4 is 16, so we got to carry that 1. 4 times 1 is 4, plus 1 is 5, 56. 1 times 4 goes in this column. 4, 1 times 1 is 1. We get 6, we get 9, we get 1. Now that's pretty close to 200. I'm pretty satisfied with that. I don't think I need to try another one. But just for fun, if we want to prove it, let's look at what we mean 15 squared. Do we think it's even going to be close? I know it's not going to be close, but let's just do it for fun, okay? So 15 times 15, 5 times 5, 2, it's 25, carry the 2, 5 and 1, plus 2, 75. Times 5 is 5, 1 times 1, 1. Wait, did I mess something up? No, I didn't. 5. 7 plus 5 is 12, so we carry the 1 here. Now we get 225. All right, so 225 is not that far away from 200. It's bigger than it. It didn't say it had to be, it's just got to be closer. So it doesn't matter to which side of 200 is, whichever one's closer. This is 4 away from 200. This is 25 numbers away from 200. right? 200 would be somewhere in the middle. So this number, which is closer to 200, if I take the square root of that, since we got that from 14 times 14, my square root of 196 would be 14. So my answer to this problem is 14. So here's our number line. We're going to write that in, 14. That's our final answer. That is a whole number. It's a square root. That approximates the square root of 200. And in order to see this, let's get rid of 13. That wasn't really very close. So let's just extend this number line here a bit, okay? Just in case this helps you to see why this makes sense. Okay, so there's 10, there's 11, there's 12, 13, 14, and 15. Okay, so we said if we square 13, oh, I've forgotten already. What was it? You know what? Doesn't matter. Let's square 14 was 196. 15 squared is 225. And we're looking for the square root of 200, which is like right there. It's very close. So when I take the square root, it's going to be something a little bit bigger than 14. So if we use the square root of 196, which is 14, that is a good approximation. It's a whole number, and it's going to be close to whatever the square root of 200 is. Okay, so that's our answer, 14, and we're moving on. All right, question number 11. Okay, so what is 150% of 60? There's a couple ways to do it. I know the answer key does it a little bit different. I'm going to kind of just do this in decimals, because we can use it this way if it's something less than 100%, if it's greater than 100%. If we convert our percentage to a decimal, when converting decimal to percent, we move our decimal 2 places to the left. We don't see it here, but if there's no decimal, it's right at the end of your number, right? So we move that over. So 150% as a decimal is equal to 1.50. Oh, and we don't really need that 0 there because we're going to multiply this. But so it's 1.50. When we see the word of, we can think that we're multiplying, okay, times that number. So this means 150% as a decimal, 1.50 times 160. Or sorry, 60. I don't know why I said that. Okay, times 60 will give us our answer. Okay, so we could just do some multiplication. However you like to do that. 60 times 1.5. So 5 times 0, 0, 5 times 6 is 30. 1 times 0 is 0 in the next column. And 1 times 6 is 6. So we add that up here, we get like 900. But how many decimals did we have in this multiplication? We can count up the decimal places when we multiply. There's only one decimal place here. So I'm going to put that right there. And I get 90. So 90.0 or just 90. I don't really need to see that decimal if it's 90.0. So my answer here is 90. Now, speaking of doing it this way, if I had kept my 0 there, now I might think, oh, I've got 2 decimal places, and then I go in here and I multiply this 2 times. But that 0 here doesn't really mean anything. We don't want to put that in here when we're multiplying if we don't need to. Okay, I could write 1.5, 1.50, 1.500, 1.50000. It doesn't change anything after our decimal. Okay, that just says we have 5/10 or 5. It says 5/10. That's 5 100s. That's 5 1,000s. That was 50. I think 50,000 100,000ths or something like that. But as an equivalent fraction, it's all the same. So we don't need to represent it like that when we're multiplying. If I did this, I would need to have like another placeholder for my 0 here. So I would end up getting an extra 0, and then I would move it 2 decimal places, which is silly. So if you're going to do it this way, just make sure that you if there are any extra zeros after your decimal place, you don't include them in your multiplication. It'll just confuse you. So let's just go back to the way things were. Oops. Oh boy. Oops. Okay. All right. So answer is 90. Um, Honestly though, on the answer sheet, they do it differently, and it's a nicer way. I do like, if I do this with decimals, it might just be easier for some people to keep straight if we always have the same kind of procedure. But let's just do that quickly here. You could check the answer sheet for how they did it. They said we've got 100% of something, of 60, and then we can break this up into parts that we can kind of see and do some mental math, right? 100% of anything is always the same thing, right? If I owe you $60, I'm going to give you 100% of what I owe you. I'm giving you the whole thing. If I only give you 60% of, or 50% of something, that's going to be half of it. Okay, so if we have 100 and 50%, we can kind of calculate these separately, then add them, and then just sum them together, and you get 90. So that's actually a lot quicker. So I think that's also a very good method for a question like this. You know, if you were doing something like 47% of, I don't know, some weird number, let's say 27, then you would really want to make sure you're using these decimals, right? That's going to be a lot easier to do if you had to do that without a calculator. It's just going to be easier to think of like that, in my opinion, instead of breaking it up. But there's many different ways to do a problem. So if you like breaking it up like this, actually a really good way to do it. Okay. All right, let's do question number 12. So 200% of something. Let's do it the same way as on the answer key. So if I have 100% of something of 300, that's the whole thing, right? If I have 200%, that means I have another 100%. Okay. So I have another 300. Those together would be 200% if I added them up. So if I add these together, that's going to give me my 200% of 300, which is twice the amount. Okay, so I get 600 as an answer on that one. All right, let's keep moving on. Okay, in simplest form, what is the value of this expression? So we got to think of order of operations. There's a couple ways to do a problem like this. One thing I notice right away is I see I've got a 4 in my denominator here. And if I can do things to kind of get rid of fractions, I'm going to want to do that. So same as when we have a problem like with x's and we're solving, we've done distributive property. We can do that with numbers as well. We could add these. We could convert 2 into a fraction, add them, and then multiply by 4. Or we could use distributive property. So I'm going to do the distributive property way. And when I multiply this, I get 4 times 2. So my first part is going to give me 8. 4 times 2 will give me 8. And then 4 times 3/4. So think about that. 4 times 3 over 4. When I have that here, I can cancel my top and bottom, right? Because this is same as saying 4 over 1. If we have a 4 on the top, if we're multiplying, if we're strictly multiplying, there's no addition, subtraction going on there. It's like having 4 divided by 4. If I divide those by 4, divide by 4 on the top, divide by 4 on the bottom, I get a 1. And then 1 times 3 would just give me 3. 1 times 1 is 1. 3 over 1 is 3. So we don't really even need to see that, right? It's going to give us 3. So if I have 4 times 3 over 4, I know I can just go and I have a 3, right? So I've gotten rid of that denominator. So 4 times 2 gave us 8. 4 times 3/4 gave us 3. And now we just add. Done. Okay, 11. If you did it the other way, it would work as well. So let's just do it quickly so you can see there's more than one way to do this. So I could also say 4 times whatever's inside here. And I know I need to, in order to add this 2 to the 3/4, I'm going to have to make a fraction. So when I have 2, it's the same as if I had 2 over 1, right? 2 divided by 1 is still 2. I want a common denominator. That means I'm going to have to multiply top and bottom by 4. Okay, so that would give me then what? That's going to give me 2 times 4 is 8. 1 times 4 is 4. So now I have this. Okay, so now I can add these. Now I've got 4 times 8 plus 3, 11 over 4. Now I've got a similar situation as before when I multiplied my 4 to my 3/4. I can cancel these two, right? Because, divide by 4, divide by 4. It's like gives us 1 and 1. 1 times anything is the same. Anything divided by 1 is the same thing. So in other words, we can just cancel that and we get, again, the same answer. Okay, number 11. Moving on. Let's do one more. Then we're going to break. Okay, question number 14. Simplify, then evaluate. So evaluate means we want the actual number. If I have this and I say evaluate, I want to know that this is equal to 9. If I have something like 3 squared times 3 to the power of 3, and I just say simplify only, that means I want to combine terms where I can, so I know I've got the same base here. When we multiply powers with the same base, we know we can add the exponents. So I would get 3 to the power of 5, and I would stop there if it only said simplify. But it says simplify and then evaluate, okay? So we're going to simplify, and then we're going to get a number after. Okay, we're going to evaluate that. All right. So quick reminder of a few rules. If I have something like this, if I have a power to another exponent, we multiply these two numbers. So we say we get 4 times 2. Okay, we multiply when we get that. So 4 times 2 is 8. We would get 8. If I had 3 to the 4 times 3 to the power of 2, same base, but we're not, it's not a power. We just have two different powers next to each other with the same base. Then we can add our exponents. So 4 plus 2, here we would get 3 to the power of 6. Also, if we have something like 3 to the power of 4 divided by 3 to the power of 2, we subtract. Okay, so multiplication like this, we add. Division, we subtract. So I would get 4 minus 2. My answer would be 3 squared. If we see something like this, 3 to the power of 4 over 3 to the power of 2, that's the same thing. This is just another way of writing division, right? So again, we would have 3 to the power of 4 minus 2, which would give us 3 squared. Okay, so just a quick reminder, let's go at this problem now. All right, so here we go. Let's just start right here. So we have 3 to the 4, all to the power of 3. So we can multiply those. So let's do that first. So we get 3 to the power of 12. And then we still got time multiplied by 3 to the power of 2. So remember, BEDMAS, right? We're doing exponents first, brackets, and then we'll do our other multiplications here. On the bottom, I have 3 times 3 to the power of 10. Actually, let's do that step. Let's do that. No, we'll leave that, and we'll do it after. Okay, so 3 times 3 to the power of 10. Oh, God. Gosh. Oh, gosh darn. Okay, here we go. 3 to the power of 10. So now we have two powers with the same base multiplied to each other. We can add the exponents. So we get 3, 12 plus 2, 14. And here, again, remember, if we don't have the power here, if we don't see the exponent, it means it's 1. Okay, so let's just fill that in. Now we can add. It's easier to think of that way, probably. So 3 to the 1 times 3 to the 10, 1 plus 10 is 11. Okay, we're almost there. So now we have this division situation. So we're going to subtract exponents. So we're going to get 3 to the 14 minus 12. So 14 minus 12 is 3. We're done simplifying, but they want us to evaluate. Okay, so 3 to the power of 3 If you know some of your cubed expressions already, you might know the answer is 27, or we can write it down as 3 times 3 times 3, right? So that means 3 times 3, we get 9. 9 times 3 gives us 27. So there we go. Answer is 27. Okay, taking a quick break and on to question 15.